next speaker, Sayed Ali, oh, hang on with me, Tabayedai. He's working for Anapaya Systems AG as a software engineer based in Zurich, Switzerland. He recently finished his PhD, congrats for that, in network security from the ETH, working with Adrian Peric. And during his PhD, he worked on, wow, another Scion, another ex-Scion member on path-aware internet architecture.
So, hello everyone, good afternoon. Yeah, this is Sayed Ali, and today I'm talking about our paper, Interdomain Routing with Extensible Criteria. This work is with collaboration with my colleagues at ETH and Tecnico Lisbona. So, what does that even mean? Does this work? No? Doesn't work. Okay. Yeah, what does that even mean? So, what we mean is to optimize interdomain routes for diverse criteria to accommodate the change of criteria in a timely manner. So, what for? So, the end goal is to accommodate the diverse and evolving communication quality criteria of different applications. So, I'll make two examples here. The first example is about the diverse criteria. So in this topology, let's assume there are endpoints in AS1 that want to communicate with servers in AS5 for a file transfer application, which needs high bandwidth path. And at the same time, there are some other endpoints, or there are some other applications that want to, that have a VoIP application that want to communicate with servers in AS6. For VoIP application, we need a low latency path. Also, these criteria can evolve over time. For example, let's assume if ASs start to advertise numbers about their carbon intensity of their path. So some endpoints then wants to reduce their carbon footprint of internet use, and then they switch to paths that are greener. So here, the question is that, we cannot do this with BGP because BGP has stateful forwarding and a restricted forwarding state. So having multi-criteria path optimization usually requires to keep and store multiple paths for destination, which clearly does not scale in the restricted forwarding state of the border routers. Also, BGP cannot compute optimal paths for general metrics, but it computes an equilibrium of path. And also, we know that the path selection logic of BGP is ossified, has not changed for a long time, and it's quite rudimentary. So far, to accommodate these diverse criteria, people have been using WANs or data center that are operated by a single entity. So, for example, the Meta Express backbone, Microsoft Swan, or Google B4. So data center networking enables path optimization. However, there are single entity solutions. They are difficult to run in a global multi-stakeholder environment. And there are scalability problems with them. So nowadays, the data center networks are starting to use back BGP, even in the WANs, bringing back all the limitations of the BGP. In this work, we look at the potentials of a path-aware network as a federated alternative to achieve multi-criteria path optimization. Simply because these path-aware networks enable path optimization at endpoints by providing multiple paths to them and let them select one of those paths. They are scalable to a large diversity of paths because of the stateless forwarding. And the packet carried forwarding state reflects the decisions made by the control plane and the endpoints. So first, I will give a short overview of how routing and forwarding works in path-aware networks, especially in SION. So first, we have the routing. So in the routing, all the ASs have something called the control plane service, or for short, control service. The control service of each AS starts the routing by advertising a route to itself. These paths propagate across the network. Each AS adds its own AS hub, and when they arrive at an AS, for example here at AS 1, the control service at this end AS registers this path, and we have the second phase. In the second phase, the endpoints request the path, for example here to AS5, and then the control service provides them with a set of paths with to the AS5. The endpoint then selects one of these paths and puts them as in the packet header of the packets that they send. And the routers adhere to this path that are in the packet headers. So the question is that why do we need to do routing with extensible criteria? Or to clarify, isn't path selection at the endpoints already enough? We argue not. So because of two reasons. First, scalability. So there are super exponential number of paths in the internet that does not allow providing the endpoints with all possible paths. And on the other hand, we have a problem of optimality. So if we decide to provide an arbitrary subset of paths to endpoints to select from, then we can, it can result into a suboptimal path. So for example, in the relatively small SION network, or SION education network, Sierra, we see a median of 100 paths from ETH Zurich to all other ASs, and with 400 paths. But are all these paths useful? We don't know, probably not. So there might be that a lot of these paths are not good paths for the endpoints. And the other problem is that there might be some interesting paths for endpoints that are filtered out by a rudimentary routing system. Therefore, we need routing on multiple optimality criteria. The algebraic foundations of this has been laid by the work of Sobrino and Ferreira in SIGCOMM'20. And in this work, we seek to realize these foundations in the SION path-aware internet architecture with an emphasis on the extensibility of routing criteria. So in this work, we asked two research questions. The first is how to make interdomain routing aware of application criteria on which it needs to optimize path. And the second is how to extend the routing criteria, which means how to add new criteria or remove the older ones. In answering the second questions, we first identify four main problems to the extensibility of criteria. First and foremost is standardization, which can delay the deployment of new features by years or a decade. Then comes the development by vendors and deployment by ISPs, which can also cause a huge delay. And once all these features are developed and deployed, there can be inconsistencies across implementations by vendors or deployments across the network. And finally, whenever we want to update the control plane logic, we probably need to interrupt these control plane sessions between routing nodes. So to overcome all these obstacles and reach our final goals, we set four concrete goals. First, interruption-free addition or removal of criteria. Second, independent development and deployment of criteria by each AS. Third, automated and instant agreement on new criteria among all ASs. And enabling end domains to express their routing criteria to the network. For the first two goals, we propose orthogonal path computations. And for the last two goals, we introduce on-demand or reverse on-demand path computations, which build on top of the orthogonal path computations. But first, let's look at what we mean by this. So orthogonal path computations simply means to run multiple path computations in the network in parallel without interfering each other. So for every AS to participate in each of these computations, they need to deploy the selection function that is associated with each of these path computations. For example, here AS2 deploys two selection programs, one that optimizes paths for bandwidth and the other that optimizes paths for latency. So whenever the routes that are, for example, originated from AS5 and AS6 arrive at AS2, the AS2 simply provides all of these paths to both of the programs, and the program for bandwidth selects the bandwidth optimal path, and similarly, the latency one selects the latency optimal path. To guarantee optimality, all the ASs need to deploy all these selection programs. To add a new criteria, every AS needs to simply add the associated selection program, and to remove criteria, they can remove it without interfering with other path computations. Therefore, these selection programs allow for interruption-free addition or removal of criteria. They allow for easier and faster development and deployment of criteria. And finally, they allow for deployment of non-standardized programs. So now I will look into what on-demand or reverse on-demand path computations mean. So on-demand path computation means to compute paths based on the criteria of end domains. So for example, here, AS5 attaches a selection program that optimizes paths for bandwidth to its routes that it originates. And also AS6 does the same, but with another program that optimizes paths for latency. When these routes arrive at every AS, for example here at AS2, the AS simply deploys this program, provides the path to the program, and the program selects this path out of the path to the AS5 and propagates it further. Similarly, they can do it for latency for paths to AS6. So these programs substitute standardization. They are deployed fully automatically, and they ensure consistent implementation and deployment across the network. But what is reverse on-demand path computations? It's very similar, but it's in reverse direction. So for example, it can be with the criteria of the source of the traffic. So it computes routes from one domain to any other domain, which is in contrast to traditional routing, which is from any domain to one specific domain. And it's very useful for optimizing reverse paths, for example, from server to client. So for example, in this topology again, if the forward path from AS1 to AS5 is optimized for bandwidth using an on-demand path computation, the reverse path, for example, for acknowledgement messages can be optimized for latency using a reverse on-demand path computation. So we have introduced all this, but the main question here is that how do ASs know what path computations they need to deploy? So we propose a deployment model consisting of 3 categories of path computations. The first one are pre-configured and standardized ones that we assume that all ASs should deploy. And the goal of this level is to just establish basic connectivity. And on top of this, ASs can also deploy pre-configured but non-standardized or maybe standardized ones that optimizes paths for a basic criteria that each AS thinks that the neighboring ASs or the other end domains may be interested in. And finally, we have the on-demand layer, which optimizes paths based on the criteria of end domains. As we go up in this pyramid, the essentiality and priority of these path computations are decreased, while the extensibility and optimization is increased. To realize IREC, we have changed the control plane service of Scion to this new version, which has 3 components: the ingress gateway that receives path, SPCs or selection program containers that run the selection programs and selects the path and provides them to the egress gateway, which propagates them to other ASs. The selection program containers, or SPCs, are isolated environments that run these selection programs that are eBPF bytecodes and are run within a uBPF VM. We designed 2 types of them: static ones for the pre-configured selection programs that each AS wants to deploy locally, and the selection program and the VM are there for the lifetime of the SPC. And we designed the dynamic ones that are for the on-demand path computations. So they create this uBPF VM and run the selection program for every set of paths that they receive with a specific program, and then they destroy it and they run it again for another set of paths. We have implemented a proof of concept of this idea by reusing some of the parts of the old control service for the ingress and egress gateways. And we have implemented an SPCs in Go and implemented a selection program in C that has the same selection logic as the old control service for the sake of comparison. And we have emulated it with a Katara emulator in Kubernetes cluster on a topology of top 15 ASs in the Kaida topology with 600 links. So our results show that the performance of our design is either better or similar to what we saw in the old control service of Scion. So for the network TX, we see that the IREC gateways send much less than the old control service with 30-second propagation interval, and similar to the old control service with 20 minutes propagation interval. And at the peak, we see that they have similar trends. This translates to similar trends in the CPU usage for both median and peak. But the interesting results here is that the SPCs that are responsible for running these selection programs, they only consume up to 1.5% of CPU, which shows that the overhead of the running these programs compared to the all other processes that needs to be run for Scion path exploration is relatively small. And we see similar trends for memory usage. So to conclude, we have argued that path-aware networks like Scion provide a promising opportunity for path optimization in the public internet. The plethora of possible paths in the internet necessitates the incorporating application criteria into the interdomain routing system, and the evolution of criteria demands routing with extensible criteria. In this work, we propose IREC that allows a real-time extensibility of interdomain routing criteria. And thank you very much. You can access our paper by scanning this or on the ACM. And yeah, please reach out to me for further questions. Thank you very much.
Thank you.
That's nice work. Interesting, very interesting. I also have a very interesting question that this work is just after the previous work. I think whether it's possible that your work can support the last work just presented by Carl. I think that work, the purpose is to reserve the bandwidth in the multiple paths routing, and this can be just take as a criteria in your work to support. So I think whether it's possible, how do you think it?
I mean, I think based on what their proposal, I think they propose a control plane based on smart contracts. If that's the case, this doesn't work because this is in band. My work is in band, but you can, of course, so you can use IREC for exploring the path. For example, so you want to find a path that all the ASs on the path support bandwidth reservation, yes. Okay? To ensure that, you need to use IREC. Otherwise, you cannot find, it's a sea of paths, and how do you want to find those paths that, to ensure that there are some available bandwidth. So that's how it can be integrated to that work.
Okay, thank you.
Yeah.
Hi, thanks for the talk. This is Brighton Godfrey from UIUC. So if I understand correctly, the AS of, say, the sender is doing, or the multiple ASs together are doing this computation on behalf of the preferences of the sender.
Yes.
Now, given that the Scion architecture gives control in the data plane for the sender, it seems like it would be possible to decouple that computation from the ASs and even sort of do it out of band in some separate service. Would that be possible? If so, did you consider a design that was decoupled from the autonomous systems themselves?
Okay, so decoupling, one thing is decoupling from the routers, that it's given by Scion that the control plane and data plane are completely decoupled. So these services are run, of course, within the ASs, but not on the routers. And that's actually what enables us to do IREC. But doing it off-band, or out of band, sorry, we didn't think about doing that. But I'm aware of follow-up projects. Probably they're not follow-ups on this one, but another, routing plane for Scion that, that are going in that direction, but not completely. I don't know if I can share more, but we can talk about after that. Yeah.
Sounds good. Thank you.
Yeah.
No, I think my questions were largely covered by the previous two.
Yeah.
Thanks.
Do we have another question? I have a short one. For example, if criteria or preference change, how do you guarantee routing stability?
Sorry, what?
If the preferences or criteria when you're doing the path, the routing change, how do you have any mechanisms to prevent from routing instability?
Yeah, actually, that's the whole idea of this paper. So if it changes, so it's automatic. So let's say the origin AS, which is the destination of traffic, is Microsoft, and they decide to, they want to change something about the criteria, how their customers want to reach them. So they just easily, because paths paths in Scion expire after some time, usually 6 hours. So what they just need is that in the next round, or they can even create new rounds after even 10 minutes. But for the sake of scalability, they just start new rounds of beginning with a new application, and that's it. Yeah, with a new program. Yeah.
No, I got it now. I missed that part. Okay, let's thank the speaker and.